Hello everyone, this is Spencer Snowling from Hydromantis, and I'd like to welcome you to today's webinar. It's the first one that we're doing in 2015, and I'm happy to report that we have quite a good slate of topics for webinars already thought out and scheduled for the first part of the year. And towards the end of the webinar today, I'm going to show you the new part of our website where you can take a look at our events calendar to see when all of the upcoming webinars and training sessions and so on will be being held over the coming months. So thank you for attending today. We're going to be talking about our membrane bioreactor model in GPSX. And so today's webinar will assume that you sort of know your way around GPSX a little bit. I'm going to focus mostly on the content of the model specifically, so that I can go through the details with you about how to use it, how to set it up, and as you may know, the MBR model in GPSX has quite a bit of complexity to it, and there's a lot of options available for you to access all of that complexity, or indeed simplify the model down and just use the appropriate features of the model for the task at hand. And I'm going to go through a little bit about how to decide what levels of complexity that you need for what you're doing with our MBR model. Okay. So my name is Spencer Snowling. I'm VP of Product Development here at Hydromantis, and I have been the fellow in charge of taking care of GPSX for the past 15 years or so, and I was, along with my colleague at the time, Oliver Schraw, the developer of the MBR model, and I've continued to sort of advance the features of that model over time. So my plan is to talk about a little bit of the model history from the point of view of, how did we get to the point where we are now with the features that we have. I'm going to talk about the various modes of the model, that being simple mode, intermediate mode, advanced mode, and talk about the various levels of complexity that are available. And then I'm going to talk about the details of those complexities. So, in other words, how, the various features in terms of transmembrane pressure modeling and so on, how those things are incorporated into the model, how they interact with the biological parts of the model, and sort of how the MBR differs from the regular activated sludge units that we have in GPSX. I will, as what I usually do, is do a bit of a desktop demonstration. I'll open up some of the menus and talk about the various aspects of the model, and then we'll run some simulations and demonstrate how it all works. And of course, as always, we will have some final thoughts at the end, and I will hang around at the end of the webinar to answer any questions that you have. If you're not familiar with the way it works here, basically there's a questions box that's in the GoToWebinar dashboard that you have, and you can type any questions that you want in there, and what we'll do is I'll wait till we get to the end of the webinar to answer them, but feel free to type any questions out that pop into your mind as we go along, and then I'll just sort of collect them up and do it at the end. Okay, so to get started, back in the day, when I first came to Hydromantis and first was involved in developing GPSX, we didn't have an MBR model at all. And what people conventionally did at that time was to use a completely mixed CSTR and then follow that up with a solid separation unit. This is the sort of the generic dewatering unit that we have in GPSX. Of course, you're looking at the older versions of the icons from the software, the flat ones here. And we would then have to put in a recycle here to, take the solids that were being held in by the membrane and then put those back in the tank, and then you, of course, would waste some out along the way as well. And so that became sort of the conventional way to do it. However, we had a lot of requests for a bit more sophisticated model at that time, where you have some sort of membranes that are submerged into the tank along with biological activity. And thus was born the MBR model. We have two different versions of those, and they came along in version 4.1 of GPSX, which was indeed about 10 years ago. We have a completely mixed version and a plug flow version of the membrane bioreactor. you can see it's essentially supposed to represent the same kind of completely mixed tank that you would have in GPSX with the aeration and the biological reactions and so on. And then we also have a submerged filter in here to do the solid separation. And then you can take the filtrate out through the specific connection point there. And then hopefully all the flow goes out there and you're not overflowing any out the top connection point. And then there's a pump connection point, as we have with most of our activated sludge units. The usefulness of the plug flow MBR is that you can actually take BNR type configurations where you may have several reactors in series with some internal recycles or some other sort of sophisticated feeding, and then put that all together into one object. So you can do it either way. You can have a bunch of CSTRs with one of these MBR units at the end, or you can do it in the plug flow. It basically works out to the same thing. So first of all, I'll mention that our MBR model is there and it's doing solid separation, and we're doing the formation of the solids on the surface of the membrane, forming the cake. And that formation of the cake and the way that the flow moves through the membrane is assumed to be the same no matter what the configuration of the surface is. So in other words, whether you're using a hollow fiber type membrane or a flat sheet type membrane, the model is going to basically be the same. It's going to act in indeed the same way, and the amount of flow going through and the amount of solids being captured will be done the same way. Really, all the model cares about is how much total surface area do I have and what is the capture rate. So the MBR object, when you put it on there, it basically consists of several components. We, of course, just like any of the unit processes, have a hydraulic model. And just to be clear, by hydraulic model, I mean we're doing a flow balance, and we're keeping track of the flows in and out and the changes, if relevant, the change in the water level in that tank. We have the biological model, of course. That's the good part, the part that does the nitrification, denitrification, COD removal, BioP, and all the other stuff. We have an aeration model, which is going to, as I'll show you a bit later, is a little bit customized for the MBR model. And then we have the filtration or solid separation unit that's in there as well. Now, one of the things that you'll notice right away, the very first menu that you find when you open up the menu for the MBR unit is that there's this model options menu. And these various options here, in terms of the way that we do the hydraulics and the filtration and some other subsequent things like backwashing, these can all be turned on and off as needed from this menu. So the subsequent menus that I'll show you will look a little different depending on what you have turned on and off at any given time. Basically, it boils down to wanting to know if you want to have the TMP, the transmembrane pressure calculation on, and the backwashing and so on, all that stuff to do with the formation of the solids on the cake. Or do you also want to have the volume of the reactor itself be variable? By that I mean the liquid volume. Do you want us to actually do the detailed calculation of figuring out how much water is coming in for each backwashing unit and then have that volume go up and down and so on? So I'm going to run through a few slides here that will sort of discuss when is appropriate to use each of these different types of modes and sort of the highlights of those. So when you're in simple mode, now this is the default mode that you will be in when you first put the object on the screen. The default mode is simple, meaning that we're not doing any backwashing. We don't actually model the solids being formed into a cake and put back into the solid, back into the situation at all. In this case, we're just going to be doing the biological part only and the oxygen transfer and basically doing the activated sludge part. We will have the appropriate level of solids kept in the system as part of the the model itself. You specify the capture rate, which would be 99.9% or something like that. But we don't actually figure out how much of that is sitting on the cake and how much of it is in the liquid. We basically assume that everything is in the liquid. It's all been successfully captured and returned to the bulk liquid. So this is basically for situations where I want to model the biological part of an MBR, but I don't want to look at all those physical details. So we make the assumption in simple mode that the filters operate without any problem. They don't get clogged, and we don't have to worry about backwashing or cleaning the filters or anything. Basically, we assume that everything works the way that it's supposed to work, and we let the model just assume that's fine, and then we concentrate on modeling the activated sludge portion, but we want to be able to do it in an MBR context, which is why we have it set up for this particular system. So this is by far the most common usage of the MBR model in GBSX, is to use it in its most simple format. It allows you to do tank sizing. It allows you to calculate the oxygen transfer and the amount of energy that you're using to do that. Sludge production, of course. Basically, any other aspect of the biological activity. If you're setting up a biological phosphorus removal system that incorporates MBRs in it, then you could do that very easily here with the simple mode, and you wouldn't have to worry about some other details. Okay, so now moving into the intermediate mode, we're going to flip that first option down to backwash and TMP calculation. And by TMP, I'm referring to the transmembrane pressure, the amount of pressure that it takes to pull the flow through the surface, through that cake layer that's formed there. And there's a certain amount of resistance that's calculated from another model, which I'll have some slides on a little bit later. So in this case, we are going to be assuming that the flow that's coming into the system is going to be flowing out, but we actually are going to go ahead now and figure out how much solids are into that cake. By that, we want to do a mass balance of the solids that are captured going onto the cake, and then they get returned back to the liquid when things are backwashed or relaxed or scoured off by air, or just basically diffused back into the liquid, or detached back into the liquid. So this allows us to basically model everything that simple mode does, all that biological activity and oxygen transfer, plus actually take a look at how much pressure is required to run this particular system. So we are making the assumption that flow in equals flow out in this particular situation. So we are showing the flow coming in, and there's a certain amount that you're going to be taking out down here, potentially for doing mixed liquor control, the amount that you're going to be wasting, so to speak, and then basically the membrane flux, the amount of permeate coming out of that system is equal to the flow in minus the amount that you're pumping out down there. And it's kind of flow in equals flow out. That allows us to take away a lot of the, one other degree of freedom that you would have to worry about. We just assume that all works the way it's supposed to work. But at the same time, we are going to allow you to figure out how much energy is required to be able to run this particular system. So in addition to all the things that we had before, tank sizing, oxygen energy usage, and sludge production and so on, we now also get some estimation of how much of those solids are captured on the surface, and that what transmembrane pressure needs to be applied in order to get that flow through that membrane. Okay, now the last of the three is the advanced mode. This is where we're going to basically take everything I've already said, and then we're going to add on to that we're going to allow the model to vary the volume in the tank. So in other words, you can pump the tank down and then let it fill up during the backwashing mode, for example. This is the most advanced version of the model. This is basically all the bells and whistles: biological activity, oxygen transfer, cake formation, transmembrane pressure estimation, and full control over the flux. Now, the way that works is, because flow out is now not assumed like it is in the other two modes, you actually have to figure out the right TMP to get the flow out. So basically, you put a controller on it, or you specify a certain flow rate. And now TMP is actually an input rather than an output. So you apply a certain pressure. We calculate via the resistance models and other things here how much flow actually is going to come out. And if your flow out is less than your flow in, then the tank will start to fill up a little bit. So this is actually the most common, or pardon me, the least common. It's the most advanced. It's the least common version of that, of the model. And if you turn on all these bells and whistles, you'll find that you're getting TMP TMP is now an input rather than an output, but it does allow you to have very advanced control over the flux and to look very interestingly at the dynamics of the system in a very short time scale to see what is happening during that backwashing phase and during the phase where the scouring is happening, and looking at the dynamics of the actual system that you have. Now, I have to admit, I don't know very many people who use the model in this mode all the time. I have done a couple projects where I've done this myself, but you know, this is the most advanced and probably the least frequently used. Okay, so let's answer the question then. If I'm sitting down to do an MBR modeling project, what mode should I be using? And really, it depends on the task at hand. This is actually not just about MBRs. This is always a good question to ask yourself on any modeling project. Is, you know, how complex should my model be? It really depends on what you're using the model for. And as I always recommend in all of our training sessions, try to simplify your life if you can. Go with the simpler models if they support the questions that you are trying to ask, if they will give you the information that you need for the task at hand. So I made this little flow chart here that helps you make a decision about you know, which version of the model do I need to use. The question you need to ask yourself right off the bat is, do I need to know anything at all about how the filter works? You know, do I need to really understand anything about the pressure and so on? And if the answer is no, then use simple mode. And that's what most people do. If I do need to know a little bit about that, or I am you know, curious about how this system works, the next question you ask yourself is, do I really need to look at the dynamics of the water level going up and down in the tank? If the answer is no, then go to intermediate mode. You'll get your TMP and backwashing calculations, but you don't need to worry about the tank going up and down and having to have, you know, a flux controller built into it on top. And if you do need to know that details of the water level, then of course turn everything on, and then you're using the full modeling artillery here. Okay. So now I've sort of given you this feeling here that we've got all these levels of detail. Let's talk about what's actually in there. Let's look under the hood, so to speak. So I mentioned that we have the hydraulic model, the biological model, the aeration model, and the solids filter, or the solid separation unit model that does for the filtration. And so I'll deal with those in that order. The hydraulic model is basically keeping track of the flow that comes in and out. And so you know, we have flow in, we have the flow being taken out through the wastage, we have the flow that goes out through the permeate, and we also have, in addition, backwashing that happens when you use it in the more advanced modes. So different elements of this will apply depending on which version of the model that you're using. So in all modes of operation, in all your simple, intermediate, and advanced, we obviously have a flow coming in that you either specify or is calculated from something upstream in your model, and we have the wastage. You can either specify that directly, or you can manipulate that by a PID control loop. And as you know, that works basically exactly the way that it does in a clarifier, or if you have a control splitter for doing your wastage outside this particular unit, all works basically the same way. Okay, now in simple mode of operation, we're not doing backwashing, so this is not actually relevant in our equation. And the permeate is basically calculated by the flow balance. So we are able to assume, and in simple mode, that there's no change in the volume. So our dV by dt over here is 0, and we just calculate from subtraction. Okay, now moving on to the more advanced models are basically, if you have an intermediate model, we are actually calculating some details about the permeate here. We're calculating the amount of solids that are on the filter and what the resistance is and how much pressure is required. And we do some estimation. Now in intermediate mode, we're still keeping this flow in equals flow out, no change in volume aspect. But we do have some backwashing, and we take that into account. And then we have our permeate that we're going to calculate as well, or pardon me, calculate by difference. And that allows us to use all the terms in this equation. In advanced mode, this part is actually calculated from your application of transmembrane pressure. And in that case, our dV by dt could be anything, and your volume can go up and down. Okay. So basically, flows in, flows out, keep track of everything that goes in and goes on. Next, moving on to biological model. Basically, we use the same model in the membrane bioreactor that we do in any of the other activated sludge models in GPSX. So, of course, you have ASM1 and ASM2D and ASM3 New General, all of those ones that we've had for always. These are all available in the MBR objects. And then, of course, our own in-house models, Mantis and Mantis 2, and if you have the greenhouse gas library, Mantis 3 will also be available for you to use in those libraries, so you would just select them accordingly as usual. Now, conventional activated sludge models are actually applicable to MBRs. There's a fair bit of research in the literature that said the structure of the model itself is totally valid in an MBR context. However, you may find that there are certain influent or kinetic parameters that require adjustment. Now, I've put a note on here that you can see a couple of papers that are referred to, and if you'd like me to send you these references, just send me an email after the webinar. There are times when people feel that the flock formation in an MBR is different than it is in a conventional activated sludge system. So therefore, that does affect the biological kinetics. In particular, there's some evidence to show in a lot of situations that the half saturation coefficient for things like soluble substrate or ammonia might be different in an MBR than it would be in conventional activated sludge because the diffusion through the size of the flock is a little different. So now my personal experience with doing a number of MBR projects is it's very rare that I have to go in and make some kinetic adjustments like this. I have sometimes, but certainly it's well within the variability that you would normally see in terms of different influent characterizations and the normal sort of variability you get from plant to plant with different different biomass populations that have grown up based on different waste streams. So, so yes, there's some evidence, sort of in an experimental context, and that does support the concept that you can still use the model but make some kinetic adjustments. However, it's, to be honest, nothing out of the ordinary with what you would normally do in a conventional activated sludge system. One other thing that the model does do with respect to soluble components, we may make the assumption that, of course, all of the soluble components, your oxygen and soluble substrate and ammonia and everything, that goes right through the filter and is not retained, with the exception of soluble inert material and soluble colloidal material. And it depends on which model you're using. If you're using the old models like ASM1, it's just the soluble inert, but the colloidal stuff comes in relevance if you're using our comprehensive model, Mantis 2. It's not a big deal. It just means that you're holding back a little bit more COD into the system. And of course, with Mantis 2, that COD that you're holding back gets sorbed onto that biomass and then undergoes some transformations to become available to be, readily biodegradable to be used by the biomass. And you can control that here. It's only holding 10% back by default, so that's not a great deal. Okay, moving on to aeration. Basically, like everything else in GPSX, our aeration models are based on the US EPA design manual, the fine pore aeration one with the purple cover, if you're familiar with it. Basically, it's the same thing that you would find in the conventional activated sludge tanks, with a few changes that we have done specifically to make it more like an MBR. So things like oxygen transfer efficiency and default alpha values and that kind of stuff. Those things are now actually being calibrated differently by default in the MBR unit than you would find in the regular tanks. One thing I will mention as well is just recently we updated the tuning for the DO controller in the MBRs, so it is now also different than what you would find in the conventional activated sludge tanks. So, and lastly, we've actually added on a whole second source of air. As I'm going to show you here in a moment, we have coarse bubble air being used to scour the solids off of the surface of the membrane. But it's important to be able to also account for the oxygen transfer that comes from providing that air to this biological system. So we actually have two separate places in the model where you will see that those things can be entered into the model, and we do two separate oxygen mass transfer calculations, and then that gets totaled up, and that's what gets pushed over into the liquid. Okay, so lastly, looking at that filtration model, the solids removal is basically specified. It's a very empirical model. We haven't gone to the level of detail of doing, particle analysis or anything to determine how much solids are retained. We assume that it's going to be some straight-up percentage of the concentration. By default, it's 99.9% of all the solids are held back. And then we calculate the permeate flux based upon how much solids are on the surface. So I've got these animated slides here that I can use to sort of give you a graphical, intuitive version of what's going on in the model. So now, of course, this is a gross oversimplification here of flock size and other things. But if you can imagine, we've got some bulk liquid on the left, we've got a filter surface here on the right, and our flow, when we're filtering, is sort of going through there and up and out of our particular system. So as the filtration happens, the flocks are drawn to the surface of the filter, and 99.9% of them are captured, and you get the odd one that makes its way through. Again, that's a simplification, but I'm sure you understand what we're getting at. When we're doing backwashing, we stop the filtration. We can actually do relaxation as well, just by stopping the filtration and not doing any backwashing at all. But if you are backwashing, a flow course, of course, comes the other direction, and then you're pushing off those solids back into the liquid as well. So now, when we're doing cross-flow air for scouring, you can find that as air is being provided in terms of bubbles that flow up over the surface of the membrane. And in the model, we calculate a certain mass transfer rate of the solids, and it's proportional to the amount of air that you're providing, and it pushes some of the solids back into that system. So what you get out of that is, at any point, I'm going to know the mass of the amount of solids that are trapped on the surface. That's the thing that we're doing the mass balance on over time. So once we have that, we can then calculate what the required transmembrane pressure would be. So we can calculate what that flux is in terms of the amount of flow through this, in terms of, well, actually the units by default that we're doing this equation in are liters per meter squared of surface area per hour. And this is a function of the transmembrane pressure, the dynamic viscosity, which is something that does change with temperature, by the way. And then these three resistance. It's a resistance in series model. We have the resistance of the membrane. That's like of the clean membrane before or any solids on it. That membrane has its own intrinsic resistance. The cake layer, so that's a function of how much solids are on that surface. And then a fouling resistance, which is something that is not a function of the cake, but a function of all the other stuff that's floating around in the system that kind of permanently bonds itself to that membrane and kind of plugs it up over time. So I'll give you a spoiler alert ahead of time. We don't do this one in any great detail, and most of the time we kind of leave that part of it out. So we have a little bit of a calculation or a little bit of a model there to be able to model that cake layer. So as I mentioned, it's the stuff that comes onto the surface because we're filtering it out. It could knock back off with backwashing or scouring or just diffusing back to the system. So we can then figure out what that flow is, as I was mentioning, by taking that resistance series model and then putting it into a flow model. Pardon me, I jumped ahead there, this Kozny-Kármán equation, to figure out what the flow is through a porous media, and that's the equation that we use, and we use the resistance that we've calculated earlier. So last I mentioned that fouling resistance that we have there. It's really something that's just based on time. We have a maximum fouling resistance number, and then a fouling rate constant, and then a term T here, which is the time since the last recovery clean. So if you cleaned your membranes every 4 months or 6 months, you put that in the model, this resistance will creep up over time, and then it gets reset back to 0 when the time is appropriate. So as I mentioned, it's not a terribly accurate model, and most of the time when I'm doing my own projects, I turn this off. It doesn't really contribute a lot to the system, and to be honest, in reality, it's very much more a function of the EPS and SMP, the soluble microbial products and other extracellular polymeric substances that are generated as part of regular activated sludge growth. However, we haven't got to that level. This is part of our other modeling things that we want to be able to put in the future. So our model, they're always undergoing development, and we're making them better. These are a couple of things that I have sort of in the works for future versions of DPSX. One being the ability to take into account these various things that play a significant role in the membrane fouling, and also to provide a model that allows us to make alpha a function of the mixed liquor. It's a function of many things, alpha is, but certainly in an MBR reactor, if it's one where you're operating at a considerably higher value of considerably higher mixed liquor, there is a point at which a much higher mixed liquor starts to behave differently with respect to the formation of bubbles that come out of a diffused air system. And at that point, the oxygen transfer starts to change a little bit. And so I've seen a number of papers at WEFTEC over the years that sort of describe non-Newtonian physics and a few other things. So somewhere down the road, we'll have a good bit of information to put into that model. So lastly, I'll mention a few things you can use this model for. Obviously, one of them is design. Basically, you know, we've seen a number of people use it since MBRs are very popular for doing pilot scale studies. There's also being able to design a retrofit. So you've got an existing plant that does conventional activated sludge. You can use the model to see, well, what if we put some membranes in there? You know, what kind of enhanced performance and what kind of new capacity could we get out of that kind of system? And then always, you know, being able to compare alternatives is what, you know, the best aspect of modeling here. Being able to compare conventional versus MBR. And I've seen quite a bit of this over the years too. People doing BNR with a membrane bioreactor configuration and using a model to understand whether there's going to be any things they need to be concerned about. And of course, in a membrane bioreactor, you've got that scouring air going on there, and that can lead to sometimes unintentionally very high DO in the tank where the membranes are. And if you're recycling some mixed liquor back from that to some other part of your system, and particularly if you're trying to bring it back to a part that's supposed to be anoxic or you know, anaerobic, and you're bringing back some of that air, the model can be actually very useful to be able to identify whether that's going to be a problem or not. And I've had a couple of interesting experiences with clients where the model was able to show the circumstances under which that was going to be a problem, and then, you know, you can design and change your design or your operation based on that information. Okay, so running a little bit long, so I'm going to hop straight over to the demonstration here and just open up GPSX. This is GPSX version 6.4, by the way. Hope you've all received your versions and are using them now. So this is what the MBR object looks like. This is actually part of one of the sample layouts that we have available that you can select under our unit processes. I've modified this one slightly just for today's demonstration. And I'm going to open up the menus here just to take you through it. So under that model options, this is, as I mentioned before, the section where we can choose to have backwashing turned on or off, and we can choose to model it with a fixed or variable volume and so on. And we then have our typical physical and operational parameters as we would have with any activated sludge unit. Now you'll notice that there's two sets of them. There's one of them, there's physical, and we divided it into the stuff that's relevant for the membrane and the stuff that's relevant for the actual activated sludge tank. And then the same thing for the operational parameters as well. So the physical tank menu, that's basically the same as any plug flow tank. The membrane physical is where you would specify a number of things with respect to the properties of that membrane, including solids, capture rate, and so on. So this is where you specify the total membrane surface area when we're doing the TMP calculations. That becomes an important parameter. Right now it's grayed out because I've left this in simple mode. And other things like the resistances and so on that I've mentioned earlier. So if I go back and take a look at the operational parameters, again, for tanks, it's the same thing that you would normally see. It's where you specify your internal recycles, where you specify how you're doing control. I've got a mixed liquor controller on here with a 6,000 milligram per liter set point, and we've got a DO controller on, and we've got some no oxygen in the front, but we've got a set point of 2 at the back end here. And I've got an internal recycle here, so we're sort of more or less doing MLE to a certain degree. Okay, so let's jump over here and we'll take a look at what you get when you run this in the various modes. So I'm running it right now in simple mode. I've left it so that we're not modeling any backwashing or any transmembrane pressure or any of those other details. But you still get that biological part here. So we can see that we've got our tank. We can see that, for example, the ammonia, you know, we're nitrifying down to 2.3 milligrams per liter. We're generating some nitrate, but because we have an anoxic zone, we're doing some denitrification as well, and that's actually worked out pretty well for us in this particular system. And there's quite a bit of detail here in this these models with respect to what they show in this quick display panel here, and you can take a look at the oxygen transfer and so on. Now, because I'm in simple mode, if I go to look at how much any of the details of the filter, I'm not going to see anything because we're in the simplest mode. Right. Okay. So, and you can plot your profiles just as you would in a plug flow tank. Okay. So now let's switch over to turning on the backwashing and transmembrane pressure calculation. However, we're still working with a fixed volume reactor. So we're not keeping track of, a variable flux rate, and we're not keeping track of variable water levels or anything like that. So now we basically get somewhat similar information where we've got our controller still doing the job, keeping our mixed liquor suspended solids at 6,000. But now we can actually get a calculation here of the, this is actually the membrane flux. It's a meter squared per meter cubed per day. Meters cubed of flow per meter square of surface area per day. And so that's shown here. I'm taking a daily average. That's why it's moving up and down a little bit as we were moving up and down as we were growing a little bit more biomass as we went along. So we can get the TMP here. That's shown in kilopascals, but you can change that to whatever is your favorite pressure unit. And we can see here that's pretty much steady state as we go across. So lastly, I'm going to flip on the variable volume as well. Now, one thing I should mention about the most advanced mode is that you can't turn on, or you can't rely on the steady state solver in this case. The steady state solver is only going to give you a sort of an approximate initial condition. You really need to run a dynamic simulation long enough to let everything sort of come down to an equilibrium. The reason for that is that, of course, we have variable volume going up and down as backwashing is happening, and of course we have growth and other things happening in a sequencing type system because of that backwashing. So there really isn't a technical exact steady state. It's something that changes a little bit over time. So you need to be able to run a dynamic simulation, and we can see here that if I go to the effluent, you can see that, well, maybe we'll run that actually a little bit longer. Let's run it for 20 days. We can see that eventually this will settle down to a steady state answer, and that's ultimately the result that you get. And we can see in our filter, well, the filter has now sort of settled down, and that flux has reached an appropriate target, and we're getting the appropriate amount of flow in and out, and we're accounting for the backwashing. By the way, notice here, this is the reactor volumes. Our reactor volume in the last unit is a little bit not the same as the others because, of course, when we're in filtration mode, we're actually draining the tank down a little bit, and then we get it filled back up again when it backwashes. So that's what's going on there. Okay, so that's a really rough and ready spin through the MBR object, and you can see more details in our sample menu here. I'll just show you what that looks like. In version 6.4, this is actually a new feature. If you go to the sample layouts menu, we have this nice new dialog to browse your way through the, I believe, close to 60 different layouts that are in here now. We go to unit process examples, we have the membrane bioreactor option there.